The lightweight cooling vest, or LCV, was designed to provide personal thermal regulation for a young girl who suffers from an autoimmune condition known as anhidrosis, which causes the inability to sweat and thus the inability for the body to thermoregulate itself. While the intended end user has this condition, further applications of the product could include the elderly, who themselves are susceptible to heat stroke, and outdoor recreationalists who just want to keep cool.
The LCV is a portable cooling unit consisting of a refrigeration system cascaded with a water loop. The refrigeration system is housed within a carbon fiber shell within a backpack, with quick disconnects located here, allowing for completion of the water loop with the hydrotherapy vest, which is to be worn around the user's torso. The LCV can be turned on by means of an externally mounted toggle switch here, and compressor power input controlled via the potentiometer located here in the side vent of the backpack. Heat exhaust ducts are located on the sides of the backpack, here and here, and provide adequate airflow for the condenser while maintaining maximum discretion. If the LCV requires recharging, the battery charging port can be located here within the backpack. The hydrotherapy vest is wrapped and secured around the torso by means of an elastic Velcro strap. The backpack can then be put on by the user and quick disconnects engaged to connect the hydrotherapy pad to the backpack refrigeration system. Once the hydrotherapy vest and backpack have been put on and connected, the LCV can then be turned on via the toggle switch located on top. The refrigeration system is composed of a compressor, which compresses the refrigerant R134A from a saturated vapor to a superheated gas, increasing both temperature and pressure. A condenser, which transfers heat from the refrigerant to the ambient environment, transforming the refrigerant from a superheated gas to a saturated liquid. A capillary tube throttling device, which reduces system pressure and temperature, transforming the saturated liquid to a liquid vapor mixture, and a heat exchanger, which transfers heat from the user-worn water loop to the refrigeration system, effectively cooling the user and transforming the liquid vapor mixture to a saturated vapor supplied to the compressor, restarting the cycle. The actively powered components in the system include the compressor, the control board, the condenser, and the water pump. The compressor power and rotational velocity is determined by the potentiometer resistance input to the control board, whereas the pump and condenser both operate at a steady power input. The system is wired in parallel to supply 12 volts DC to all components and ensure all components are turned on and operational at the same time with the flip of a switch. Both the backplate, as seen here, and the shell were manufactured by the team out of carbon fiber, and the brackets that hold all the refrigerant components were 3D printed out of PLA and mounted to the refrigeration system with the components to the backplate. The shell is attached to the backplate via the riveted aluminum brackets on the sides, allowing for complete external assembly and disassembly of the housing without the need for an access port. In the case that the system needs to be recharged or evacuated, Schrader valves are located on either side of the compressor, which can be connected to with a standard HVAC gauge manifold set.
The LCV is capable of achieving a temperature within the vest down to 61 degrees Fahrenheit in as little as 5 minutes from initial system startup, and maintains cooling for up to 2.5 hours under the optimal input power to the compressor. The overall weight of the backpack is a light 12 pounds, with the hydrotherapy vest weighing in under 2 pounds. The combined weight of the product is a mere 13.8 pounds, allowing for ease of use and portability. The material cost of developing the LCV was approximately $550.
Overall, ZENK has successfully created a functional prototype of the LCV demonstrating effective portable cooling. Future modifications that can be made to increase the effectiveness, battery life, and accessibility of the LCV include the addition of a Raspberry Pi, which can control the compressor input power via a user interface app on the user's smartphone, a compressor feedback control system, which can allow for intermittent use of the compressor when certain temperature thresholds are met, thus increasing battery life over continuous use, an active throttling device, which can ensure optimal performance under various pressure ranges controlled by power inputs to the compressor, thus allowing for lower vest temperatures and increased variability and control of the cooling process, and a higher capacity battery.